Hi everyone, this is Dr. Hopkins with a video about equilibrium. So last time we talked about reaction Gibbs free energy, and we learned how to calculate these reaction Gibbs free energies at standard state, and we interpreted if they're less than zero or negative, that means a reaction is proceeding towards products. If they're greater than zero, that means the reaction favors reactants, so it'll end up with more reactants than products, and so forth. So we use the language spontaneous and non-spontaneous in those cases. And then we discussed how the magnitude of that delta G, so we calculated a free energy, we calculated it in kilojoules per mole, and then we can say, well, that shifts towards, that means we're more products or more reactants. But it also tells us how much, and we were promising a mathematical expression. And so here it is. The reaction Gibbs free energy is equal to, and we have a negative sign, so R, that's our gas constant. T is our temperature in Kelvin. Okay, Celsius has that zero in the wrong place. We can never use Celsius. And then natural log of K. So what is K? K is our equilibrium constant and basically represents the ratio of products to reactants. So it represents, hey, we've got more products or we've got more reactants, kind of like what delta G is telling us all along. So we're just taking what we knew about the free energy and putting it into this mathematical equation. Okay, so let's apply the equilibrium constant. If we have some reaction, and I've just got general A plus B, C, we've got reactants plus reactants go to products. We would write the equilibrium constant as K is the ratio of products to reactants. So in this case, we write our concentration of our product raised to the stoichiometric coefficient, which is 1, so we don't have anything there, over the concentrations of our reactants raised to the stoichiometric coefficient. So where there's a 1 and then there's a 2, and that's the power. Now, in each case, these concentrations are divided by their standard state. The standard state is 1 molar. So basically what we're doing is we're getting rid of units. So every equilibrium constant is unitless. And if we have a K greater than 1, so we're higher in products, that also means the natural log of K is greater than 0, so it's a positive number. And that would mean that our delta G, if we go back to the previous slide, is less than 0 because of that negative sign. And in this case, equilibrium favors products. So K is representing what we already knew. If it's less than 1, that means that there are more reactants than products. Our ratio is greater in the denominator. Natural log of K, so if it's less than 1, the natural log is less than 0. It's a negative number. That means our delta G is a positive number because temperature is always positive. And so we're favoring reactants. And if we have a reaction at equilibrium, it's going to stay there forever. So that's kind of one of the last things about equilibrium constant. If we've set a reaction, we get to the equilibrium, it won't change unless we add or do something to it. Okay, so let's see. How do we determine the equilibrium constant? And there's one way we can do it. We can actually run the reaction, let it go to equilibrium, and measure the concentrations of all the components, and then ratio them up, and we end up with our K. So as an example, we have a reaction here where we have silver ion in solution, ammonia reacting to form this complex of silver and ammonia. Okay, and we let that reaction run. The concentrations of equilibrium end up being 3.3 times 10 to the minus 3 for silver, 6.6 for ammonia, and then we end up, sorry, that should be a 2 here, where this is 1.5 molar. So what we want to do is write an expression for K and determine what is the value of K. Okay, so the K, if we were to write the equilibrium constant, it's products raised to their power, so the concentration of that silver ammonia, over reactants, where we have the concentration of silver and the concentration of ammonia raised to the second power. Okay, so let's plug in all of our concentrations given in the problem and solve it. So we have 1.5. Now remember, we're always dividing by 1 molar, so we're getting rid of the units, and we're left with 1.5 and 0.0033 and so forth. And so if we add those all together, we end up with, or we multiply them out, we end up with an equilibrium constant is 1 times 10 to the 7th. Okay, that's really large, and it clearly shows that this reaction favors products, as if you couldn't tell if you have a final concentration of 1.5 versus millimolar concentrations of the reactants. So there's another way to determine the equilibrium constant, and that's going back to through the thermodynamics, where we can use our delta G to determine K, right? So we know how, based on a reaction, we can determine the delta G of the reaction based on sets of or tables of the formation Gibbs free energies for each of the components. So here we have, and I'm not drawing the reaction. If you think back to the reaction we had, this is the products. So it's products minus the sum of the delta G of formation of the reactants. And I've written it out here where we have minus, and this is the stoichiometric coefficient for NH3. The other ones are 1. And then all we do is we go to a table in the back of our book and we look up these values, or we just simply Google them. And I look them up, and we have, these are all in kilojoules. Kilojoules per mole, we have negative 16.2 and so forth, and we add those up, and we're left with minus 40.17 kilojoules as our reaction Gibbs free energy. So let's use that and our expression for K to determine our K itself. So we rearrange this is the natural log, so K, and that's the exponential of minus delta G of R over RT. So we'll plug in our 40,170. R is our gas constant. That's in joules. I'm not including units to make it easier to see, but that's in joules. This is in joules per Kelvin mole, and this is in Kelvin. And then this is all minus, so that's plus. And we're left with an equilibrium constant that's 1.1 times 10 to the 7. So it's very close to what we determined experimentally. Actually, just to the least significant digit, there's one difference. It's also large, it favors products, and it's similar to what we determined for experimental. So there are two different ways to determine equilibrium constants. And actually what you'll see later on is that there are whole tables of equilibrium constants. So what happens if we're not at equilibrium? What happens if we're on our way to equilibrium? Things are going to change. So delta G gives us the final ratio. So what it's going to be when it's done and it's undisturbed at equilibrium. But how would we figure out if we're on our way to equilibrium? We have an equation where we compare to the standard state. So we have our Gibbs free energy, our reaction Gibbs free energy. This is our standard state reaction Gibbs free energy, plus RT natural log of what is Q. Now Q is a reaction quotient, and basically it's the same thing as K. It's the ratio of products to reactants, except it's the ratio of products to reactants at everywhere other than the equilibrium. So if this delta G is greater than 0, or so if it's positive, that means we have too many products. Our Q is greater than the K, and so the reaction is going to react and remove some of the products and shift towards reactants. Likewise, if it's less than 0, that means there's too many reactants, and the reaction is going to move towards products. So our Q is less than K. And if it's equal to 0, it's at equilibrium, and at that point, the Q and the K are equal. And once it's reached to the K, if we don't add anything, we don't increase temperature, we don't add any products or reactants, it will stay there. So let's do an example using the reaction quotient. So let's take our same reaction we've been dealing with through the whole video, where we have our silver and ammonia forming our complex. We're going to use the K we determined from delta G, similar to the one we determined experimentally, so it doesn't really matter. Let's calculate Q when silver is 0.01, ammonium is 0.01, and the silver complex, now once again I've dropped the 2 for some reason, is 0.5 molar. So let's figure out if this reaction is going to move towards reactants or products. And so we plug in our Q is the same as K, so it's going to be the products to the stoichiometric coefficient, so that was 0.5. Now we're dividing out our molar because we're dividing out the standard state. I'm not showing that step, but it's there. And then we have our silver, 0.01, and our ammonia, 0.01 squared. If we multiply all of those out, we end up with 5 times 10 to the 5th, which is very large. But it's still less than K, because remember it's 1.1 times 10 to the 7th, so it's smaller than this. And so this is going to react to form more products. We're still going to reduce our silver and ammonia concentrations to get more products. So reaction quotient tells us the direction of the reaction. And so the overall takeaways from this reaction, we've learned about equilibrium constant and how it's the ratio of products to reactants. It stays that way forever. Okay, it's kind of our reference. We can determine K either by having the concentrations at equilibrium, or we can just look up tables of free energies of formation for our reaction itself. And then we also learned about the reaction quotient. How can we tell if a reaction has reached equilibrium or not based on the concentrations? So until next time.